In this video, we are going to talk about solving linear systems and systems of equations, that is. A system of equations is just a set of two or more equations. There's a few different types of systems. There's independent, that intersect at one point, and they have one solution. There's consistent or dependent. I guess these are both consistent. So if it's dependent, then there are an infinite number of solutions. The solutions have to lie on the line, but we call that dependent. These are both consistent. And then there's an inconsistent system, which I will draw, maybe not perfectly, but imagine these two lines being parallel, and this is inconsistent, where there is no solution. The ways to solve this include graphing, substitution, and elimination. The most popular one is probably elimination, but we'll look at graphing and substitution as well. Graphing, you're looking for the intersection point. So sometimes this is good as far as like the system goes, and sometimes it's a little bit inefficient because if we don't land on an exact like whole number or integer, then you're not exactly sure. But let's try to solve this with graphing and see what happens. So this top equation, if I get y by itself, I get y is equal to -3 over 2x for my slope plus 9 over 2. So right away, I see a couple fractions here, you know, -1.5 and 4.5. It's not a good sign for graphing, but let's play this out. And so I have 5y is equal to -2x minus 5. So y is equal to -2 over 5x. And then divided by 5 would be -1. So if we're going to graph, we're going to look at this line and then also this line and see where they intersect. So let's start with this -1 for the y-intercept, then go down 2 over 5, and we'll go the other way up 2 over 5. 1, 2, 3, 4. I put my point in the wrong spot. 5, 1, 2, 3, 4, 5. And so we have this orange line here. We can connect those. And then our green line is at 4/5 or 4.5, 9/2 for the y-intercept, and it goes down 3 over 2. So 1, 2, 3 over 2, 1, 2, 3 over 2, and then 1, 2, 3 over 2. So it looks like they intersect right here, and that solution is 5 and 1, 2, 3, 5, -3. So right away, you can kind of see the shortfalls of graphing, where like, you know, you really have to have solutions that are whole integers to be confident. And then you might not even be confident. You say, well, it looks like that. You'd have to maybe do a little more work to guarantee it, although that is the solution in this case. So graphing definitely has its shortcomings. Substitution, the steps are here, but we're going to go through an example and look at substitution. Substitution is good when you can get a variable by itself and not have to deal with as many fractions. And this is what this notes. Works best when a variable has a coefficient of plus or minus 1. So like this y right here has a coefficient of 1. That number in front is 1. And so that means you could pretty quickly and efficiently get y by itself on this bottom equation. So that can be rewritten as y is equal to 10x minus 7. And then if you think about this top equation, 6x minus 3y is equal to 3, just rewrite that one, then you can substitute for y all of this. And then that gives you an equation with only one variable, which if you have one variable in one equation, you can solve it. If you have two variables, then two equations, you can solve it. And then not in this video, but probably later, you'll find that if you have three variables and then three equations, you can solve it. So we started with two variables and two equations, and we knocked it down to one variable in one equation. And then, there's usually distributing and some other things you have to do here. So we'll just work carefully. We can combine to get negative 24x. And then when we subtract, we get negative 18. And so x is 18 over 24, which is reduces divided both by 6 to 3/4. So now we know x is 3/4. You can plug in here or really anywhere, but you already have something that's by itself to find y. And then let's see, that's 30 over 4 minus 7. And you can use a calculator for that, or if you multiply by 4, you can get a common denominator. And so it looks like y is equal to 1/2. Subtract them to get 2 over 4, and you're left with 1/2. Or that reduces to 1/2. So, and we write it usually as an ordered pair. We won't do this here, but a good idea would be to substitute these back in to both equations and make sure they work in both equations. If they make both equations true, they are a solution. Okay, and then we have elimination, which elimination is a very popular one as far as popular method for solving systems. Then you're going to try to multiply one or both equations by something that makes these equations or the variables add to something that actually cancels. And you try to look for like the easiest one. In this example, there's not something you can just multiply once. You're going to have to multiply both equations. So let's do this top one by 4 and the bottom one by 3. And then we can eliminate y. The reason I chose to eliminate y instead of x is just because the sign is already different. So that gives me kind of one less chance to make a sign error. So we multiply everything on the top equation by 4 and everything on the bottom equation by 3. Now, one thing I would recommend is rewrite this stuff. Let's see, 1242. Don't always just rewrite both equations, even if you multiply only one equation. If you don't rewrite both equations, that's where errors happen. And then you're going to add these together. And so you get 26x, and then these add to 0. And then, let's see, 78. There. I'm just making sure that was 3. So then divide by 26 to get x is equal to 3. And then you can plug in x to either one. I'm going to use the top one because there's not a negative sign there. But it doesn't matter which equation you use to find y. So 3y. When you subtract 15, you get negative 6. And so y is negative 2. So there is elimination.